is right now in King's College in London. But Diego got his PhD in Barcelona in the University of Barcelona, and later moved to Switzerland, where he did a few postdocs in Lausanne, University of Geneva, and CERN, and later no, not University of Geneva. I'm wrong.
No, okay.
Sorry. Well, and later, so it was Lausanne, and what else?
CERN.
Lausanne and CERN. For some reason, I
spent some time in New York in between.
Okay, I thought you were in the University of Geneva in the middle. Sorry. Okay, so Lausanne, CERN. Then he joined CERN as a temporary staff member, and now he's in King's College with a permanent position. And well, the research of Diego, which I believe he's very well known to everyone here, has been focused on different aspects of modified gravity and cosmology. Also gravitational waves, black hole physics, many different aspects of gravitational research. And today he's going to talk about the new ideas to quench or detect the black hole rotational superradiance. So just before starting, as always, there will be some time at the end of the seminar for questions. And if you cannot or you don't want to use the camera and the microphone, you can just write them on the chat and I will ask them myself. Okay, thank you. And Diego, you can start.
Okay. Well, very well. Thank you very much, Mario, for the nice introduction and for the invitation. Of course, ideally, I would like to be there for many reasons, but as Enrico said, maybe spring will allow me to go. Independently of the seminar, I think I will try to go. So we can discuss all these topics and many more things. Today is the first day. I'm giving this talk for the first time. This is a working collaboration with Sam Witte, and it turned out into 2 papers. Neither Sam or myself are experts on superradiance, but we thought that since this is such a nice idea, we wanted to give it a go and see if we had something to say about it. And I think we had a couple of interesting remarks. We also have some working project nowadays, so let's see. Okay, but yeah, my point is that there may be things in my talk that are not super clear because it's the first time I give this talk. Anyway, ask please, and I'll try to answer if I know the answer. So the first thing I want to tell you about is I want to give you a first recap on this black hole superradiance, which is an idea based on an old idea by Zeldovich, okay, well, an old calculation, and then nowadays it has been revised after many different reincarnations, and in particular there is this very nice, I don't know, can you see my pointer?
Yes, sir.
So there is this very nice review that everyone knows in the field, where Brito, Cardoso, and Pani made a big effort to put together many of the aspects of black hole superradiance, but also superradiance in general. So it has been updated, even though they didn't change the archive number. There is a version from, I think, this year. Anyway, the idea here that Zeldovich calculated is that if you have a wave and it is scattered by a rotating absorbing body, well, in principle, it doesn't have to be rotating, but let's rotate it. Then what happens is that if the wave frequency that you are scattering is smaller than the rotational frequency, and here the azimuthal number of the wave that is coming in, you amplify the wave. Okay, and you amplify the wave very little, but the idea is that if you now can put a mirror and send this back to the rotating object, you can amplify again, and in this way you keep amplifying at the expense of reducing the angular momentum of the scattering object. So all this kind of amplifier. In the calculation by Zeldovich, this was a conducting cylinder. Okay. Now it turns out that you can do the same kind of a calculation and the same kind of physical process if this object here is a rotating black hole. Now what you want is a rotating black hole, but also you need some kind of mirror to bounce back this amplified radiation. And this can be provided if what you have is not a massless wave, but a massive wave. So if you have a massive wave, you can imagine that if it is not very fast, let's say, if it is not scattering with a lot of energy, it will scatter, get amplified, but then it will bounce back, okay, and in the end, kind of generate a bound state, okay, in this configuration, right? So this is what is called also a black hole bomb. And the idea, as I said, is based on this totally generic process. It has nothing to do with black holes or anything, okay? Oh, okay, very good. Now, again, from this, still in this picture from this review, if nothing else happens in this process, so you just have some kind of low energy wave scattering from a black hole, what I just told you is that you are going to generate a configuration around the black hole, right, that resembles about the state of these very low energy photons. I'm going to try to remove my headphones because maybe for an hour is going to be maybe too much. Can you hear me well now?
Yes, yes, we can hear you well.
Sorry, if the mic is not good, then I'll put them back. Okay, I put them on because the mic tends to be better. So what happens now is that you have this cloud, okay, generated around the black hole, and this cloud has some characteristics. One of them is the typical size is given by the mass. I mean the Compton wavelength. One of the mass of the cloud of the boson that you are amplifying. It has to be a boson, otherwise you cannot amplify much, right? You can do the same experiment with fermions, but then, yeah, you will never grow very much. Right? You need bosons to be able to grow number densities by a huge number. Was this a question? Or? I'm hearing some.
It's someone with the open mic. I'm going to try to mute them.
Right. So the size of the cloud is precisely given by this size of the, the quantum wavelength, and that makes sense because you are scattering very low energy bosons. So that's a typical size that you efficiently bounce back and bound to the black hole. Now, a number that is not always shown in this works is what is the typical density, and it's going to be very important, energy density of the cloud. And for this, you can take that the energy density is more or less given by the mass of the cloud. The mass of the cloud is a percentage of the mass of the black hole. You don't do anything else, divided by this cloud extent, and you get that the number densities and the energy densities of these bosons are huge. Okay, so you take, for instance, an astrophysical black hole of the size of the sun. Sorry, of the mass of the sun. You take the typical mass of this guy over there, 10 to the minus 10, 11 AV, that is going to be important. Then you see that the energy densities in this cloud are quite high. Okay, this number.
What's the number in solar masses per parsec cubed, which is what an astrophysicist?
I don't know, but you can imagine it's going to be huge.
I mean, I don't have the order of magnitude. I mean, I guess I can I'll try to do the conversion. Because when you say it's huge, you don't mean huge compared to astrophysical densities, right?
It's huge compared to electromagnetic densities that we're going to use in the future. Okay. This is the density of the cloud. The density of the cloud can be very, 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 very high. Okay. It can be higher than anything. Well, I'm going to tell you more, but it's higher than anything you have in the universe. In terms of, for instance, if this cloud is going to be the electromagnetic cloud that we're going to study in the future, you're going to generate electric fields which are way more dense than anything that you can produce in the lab, for instance.
For electromagnetic fields only?
Yeah, for electromagnetic fields.
Okay.
It depends on this mass. If this mass is very small, then it's not so large.
Mm-hmm. Yeah. Well, if the mass can also not be very, very high, right? Because if the mass is too heavy, then you don't have the cloud at all because of that condition. Yeah.
Maybe I should have put this before. So this cloud grows efficiently when there is. By the way, I put the G to 1 in all this. The Newton's constant is equal to 1 in all these calculations, as is standard in the field. So if the mass of the cloud, the mass of the boson multiplied by the mass of the object is order 1, then this process grows efficiently. If not, you can still have superradiance, but then it's super suppressed. Okay, and this is a typical order of magnitude and that's why if you have a black hole with the mass of the sun, the mass of the boson that is going to grow efficiently is given by 10 to the minus 10 eV, right? So if you are expecting to see super radiant events from astrophysical black holes, you need very small masses for the bosons. Also, you can compute how fast this process happens. So what is a typical time scale? And typical time scales, well, you can do it analytically, but also nowadays there are also numerical results that tells you that the typical time scale for this kind of process to happen is astrophysically quite short. So for instance, if you take objects with the mass close to the mass of the sun, it can happen in 100 seconds. Right? This is order 1, and this is basically what you get. So this process happens if you have these low mass bosons around. This has consequences. So in principle, this cloud it has some spin, so it is rotating around the black hole. It emits gravitational waves. When you generate the cloud, you have to take the rotational energy from somewhere, and you take it from the rotational energy of the black hole. So you are also spinning down these black holes, okay? And finally, since you have the black hole, but also the cloud around it, the gravitational field around this object is going to be it's going to be more complex than the gravitational field of just a single black hole without any other thing around it. And also it's going to be in principle distinct from a black hole and an accretion disk or things like this, right? So in principle, you will have these 3 possibilities, like this rotating cloud generates gravitational waves. It takes angular momentum from the spin of the black hole, and it also modifies the orbits around it. Okay? So in principle, you can observe this superradiance, and that's why it has been used and it has been advocated as a very interesting tool to detect very low masses. So to detect particles beyond the standard model with very low masses. Okay. So for instance, as I said, you are thinking about studying black holes with the mass of the sun. We are talking about 10 to the minus 10 eV. So are these masses motivated anywhere in the universe? Well, you know, or you may have heard that there are very low mass candidates for dark matter or for physics beyond the standard model. And in particular, 10 to the minus 10 eV lands, well, in the territory of axion-like particles or other particles that are motivated by fundamental physics. They are not exactly in the QCD axion. Also, some people are trying to do this with pions. If you have very, very massive, you have primordial black holes which are very light. But if you are thinking about astrophysical black holes, well, that's great. That this is an incredible handle to very low mass particles beyond the standard model. And those are, as I said, motivated by different physics, particular this axion-like particle from string theory or from, dilatons, these kind of things. You don't care about the spin of the particle, or the parity. You only care about the fact that the mass is very low. All right? But not only, right? See, this is order 1 result. We can have also another phenomenon having to do with the fact that you don't need the mass to be fundamental. The only thing that you need for the cloud, for this super radiant cloud to grow, is that the dispersion relation of the boson is modified as, including a mass term. So in other words, you want something to prevent the photons or the boson to propagate freely around the black hole. And this can happen and happens in principle in the universe because there is, we are living in a universe which is ionized to a certain degree, and then there is a number of free electrons floating around in the different environments. Now, you have a number of free electrons, and those are non-relativistic, and they're relatively also dilute. You know that the photons propagating around this medium will acquire at first order a plasma mass given by this formula here. Okay, this is the electroweak constant alpha, number density, number mass of the electrons for pi. And what is this number? So let's give you, I'll give you just one possibility. If the number of electrons is of the order of centimeters cube, so 1 electron per centimeter cube, that means that the mass of the photon in this medium is 10 to the minus 10 eV, right? So you had this this very dilute gas of electrons around a black hole of the mass here, of the mass of the sun, then in principle electrons would also generate this cloud of the superradiant cloud. Can this happen? Well, this is a relatively well-known number in cosmology because it's used for many different things. So let's see how this number varies as a function of redshift. Okay, and I took it from a recent paper, but as I said, this is not at all. This result is well known from before. So I'm gonna give you this number not in number density, but in the mass. So I'm gonna give you what is the plasma mass as a function of redshift. And you can forget about these wiggly lines. Let's only look at the solid line. So you see that the number of electrons was denser in the past, so this number was higher, right? So in the past, only this let's see, the black holes corresponding to these number densities are going to be relevant. Sorry, to these masses are going to be relevant. And as you go in the history of the universe, then at some point there is recombination, so there are less free electrons. They keep redshifting, sorry, they keep expanding. At some point there is reionization, so you produce more electrons. And when this happens, you see that here there is a band. This band is because in principle, you are no longer in the kind of homogeneous universe, but you are in a universe with many different patches. And this is the mean mass, but you can also be living at 1 sigma in these areas, okay? But what you see is that basically anything happening after redshift, at the redshift 100 or something, has masses which don't correspond to solar masses, okay? They correspond to higher masses, you see, because you have to saturate this condition. This is gonna be smaller, so you require higher black hole masses for this process. All right, so this is not a problem. It just means that you have to focus on other objects. But as a physical, black holes of 10 to the 2, 10 to the 3 masses, solar masses, are okay, right? They are not so exotic. This is the same plot. This is the one we did with the Sam. Well, some did most of these plots. I have to be honest. And here is the same plot, but now where we plotted the number density, and we plotted defined as the ionization fraction, mean number of baryons, and then this fluctuation. As I said, in principle, as you move in the history of the universe, if you are in the intergalactic medium, there will be an amount of free electron, but also this will fluctuate, okay, because there are many events happening, in particular after ionization, that make this number a bit bigger or a bit smaller. So this is this number, okay? If it is 1, it is the mean value, but as I said, this has some dispersion in a distribution that people kind of know. So as you advance in redshift, right? Redshift, you see that the kind of black holes that are gonna be efficiently super radiant are those that land close to 1, or within some error bars around 1, and these error bars, have to do with the distribution. The take-home message of this plot is that at very large redshift, it is big black holes that are going to be efficiently super radiant, big of this order of magnitude. At low redshift, they change by 1 order of magnitude because you have you have more free electrons. The mass is, the mass changes also, right? And then the mass of the black hole also changes. Okay, is this kind of clear what we are doing? Yeah, it's very hard to do these talks, right? Well, you don't have any feedback. So now the question is, well, all this is nice on paper, but is this really meaningful what I'm doing? Is it really meaningful assume that I have black holes living in the not in the stellar, intergalactic even medium. Well, in principle, this is not what you expect for most of the astrophysical black holes, because they have to be created inside clusters, so inside galaxies. But it's also true that some of them will be kicked out, right? In this process of generation of black holes, it is also kind of normal that some of them are kicked out of the environment where they are created, and they can even go as far as the intergalactic medium, right? So this, even though they are created at higher number density, so at higher masses, if you want, so that then they won't be able to superradiate, right? Because they don't satisfy the condition that I just mentioned before. Some of those black holes will be expelled of their local environment and will be living in the environment that I have been discussing. In these works, we focus on only one black hole, so it's not crazy to think that this happens. I think one of the things we're doing now, and it's interesting, is to understand a bit better how many of the black holes in the populations that people work with have been expelled to the areas that are interesting for superradiance. That was indeed the origin of this whole project. Try to understand this and try to see if we can do something about that. But there is also something else, is that in principle, if you have a black hole and it is sitting there for a long time, around a certain number of electrons, these electrons tend to accrete. No? If they are not very hot, they will fall down towards the black hole. So you don't expect a number of electrons to be constant, but you expect a profile. And the first people to take this seriously were Biman Barause, well, the beginning of this year. Well, it's not clear what happens, but I think the common law is that in principle there may be superradiance, but it's not so easy as if there is no profile, because it's not clear which number you have to put for the superradiant conditions and so on and so forth. On the other hand, if I am assuming that the black hole has left the local environment, I can also assume that for some time it's traveling with very high speed in the intergalactic medium, so it's not accreting efficiently. So it has left behind, if you want, the cloud that it was accreting, and I can assume that this black hole is living in a kind of constant density environment. All right, so I'm going to assume this. So both, as I mentioned in this line, both problems are in principle solved, okay, likely, if the black holes are ejected to the intergalactic medium, not interstellar. Well, interstellar is okay, but even they can be expelled to the intergalactic medium. So in principle, black holes photon superradiance happens somewhere in the universe now.
So the other limitation to another process that may hinder this photon superradiance, which is the fact that you have very large electric fields.
Yeah, my next.
Which seems that then you produce pairs, and there is this thing called the Julian Goldreich limit. So there is you produce plasma by producing positron-electron pairs. Okay.
I'm gonna go there. That's what I'm mentioning here. Is that all? Can we happily assume that photosuperradiance happens? Okay.
Yeah, I have a question. Sorry, I'm not sure if it is relevant, but I'm wondering the following. So in this process of instabilities, usually you're very sensitive to keep things in resonance, if you want. So I wonder, is it so the fact that this mass depends on the environment, so it's not really a precise. So I wonder whether if you want, the fluctuations in the electron density can change a bit the mass and maybe change the resonance. I don't know. I mean,
it can, of course. You need to assume that you are kept on resonance for these time scales. Mm-hmm. But these time scales are quite short.
Okay.
So in principle, if you are going through a very clumpy environment, mm-hmm. true that you are not gonna. But in principle, if you are on resonance for this time scale, then you're fine.
Okay.
But for instance, accretion can change it. No, if there is accretion, and then you change the mass of the. So yeah, you have to be careful with these things. It's true. So you change the mass of the black hole very fast, you are out of resonance. If you change the mass of the boson very fast, you are out of resonance. So let's come back to the comment by Enrico. So we check there are different processes that can also quench, and that's the first part of this talk. This process. So we check with some with it that, for instance, you can say that these electrons are not totally cold. Yeah, then all these plasma calculations change, but this is always negligible, so you can forget about this. Something more serious, as Enrico was saying, is that if you are at this very high number densities, so energy densities for the photons, 10 to the 36. Remember that I told you before that in principle for a astrophysical black hole, you get the cloud to 10 to the 48 for these masses. So in principle, if you get to 10 to the 36, this is the energy density at which you start per-producing electrons and positrons from just the vacuum you want. What is not the vacuum? It is huge electric field. This is the Schwinger per-production. And this is given by some rate, which is suppressed, right? Unless the electric field is very high. And this is the number that you need for this suppression to be absent, right? So in other words, if you have, before you reach the superradiant condition, right? Then you start per-producing. And when you per-produce, as Enrico said, you start changing the plasma properties, and this happens very fast. So your number of electrons are going to be higher. So you are out of resonance if you want. So you lose superradiance very fast. Okay, is that clear? So you per-produce, so the number of electrons changes, the plasma mass changes. So in principle, you quench this process. And when does this happen? Well, this happens when you have extracted a certain amount of energy from the black hole. And this amount of energy for the masses that we are interested in is very small. So you are never really efficiently extracting energy or generating any signal.
So is there a way out? Sorry, but Diego, is there a way out of this, or does this, because this seems pretty generic, right?
There's no way out unless the mass goes very low, right? The mass is very low. If you are living in a super empty, if you're living in a super empty place, yes, you can maybe, let's say.
So that's the mass at the beginning of the process, because the mass is dependent on the density, so it will change, right? So what is that mass?
So in principle, this is true. For this kind of process, yeah, this is kind of the end of the story, I think. But still, the reason why it is interesting to explore other processes is that this process is particular of electromagnetism. Other processes that I'm going to describe may be more important for other candidates for light bosons. Okay, so this process kind of kills the idea of black hole superradiance for photons. I wanted to say that even before this happens, at these number densities, energy densities, sorry, there is another process that was very recently discovered. Well, it was kind of hidden also in the calculations, but it was recently realized by these authors. That happens at way earlier energy densities, okay? At these energy densities of 10 to the 2 eV per centimeter cube. So basically when you start this whole process, what happens is that if you compute the dispersion relation in the plasma, there is the plasma mass, but if there is a electric field or a magnetic field, the dispersion relations are modified. And in particular, if there is a huge electric field already present in this plasma, you have to modify the dispersion relation by this number here. Okay, so before you had this E equal to 0, and there is a mass. If E is not equal to 0, there is this modification. What happens then is that if this is big enough, then this grows, and you can kill totally the mass. So these photons are gonna free stream away from the black hole, right? So you are living in a plasma, you grow the cloud, but the cloud grows so much that then these photons can escape. And you see, well, this is indeed the most efficient way to quench superradiance is precisely this one at this stage. And now what we did with the sun, well, we were working before this. We were working and we were about to put our paper out before this happened. Okay, so we were thinking about other processes that could also quench this process, the superradiance. And as I said before, this has also importance because some of these processes may be relevant for photons, but not so relevant for other bosons, which are not the photon, but other BSM or dark matter candidates. Okay. Yeah, that's what I told you before. That the typical energy density in the cloud is so high that before you extract this energy density, sorry, you reach it. At least for photons, you quench this whole process. So another process that could also play the same role, and we wanted to understand whether this can be dominant or not, is that in the environment of free electrons, there is also neutral hydrogen. So in principle, this neutral hydrogen, if you start producing these low energy photons, the low energy photons here will hit electrons, and through a process called free scattering, which is basically that you scatter this with a virtual photon with another electron or ion, you can convert energy of this photon into energy of this electron. All right. So you have a very energetic cloud. You can hit the plasma to relatively high energies. Well, this is nothing. It's not going to be relativistic, but these energies are high enough to ionize the neutral hydrogen. So this is basically EV. Okay. So the idea is that you have not only electrons, but also neutral hydrogen around. You can start ionizing the neutral hydrogen, then changing the plasma frequency, and then leaving the resonant condition. And indeed, the first process, the heating of the electrons, happens super fast. So that would be, we're very surprised that indeed you hit, the photon. This is the photon in the superradiant cloud. These photons living there, which are very low energy, are very efficiently absorbed by the electrons that hit very fast. And now you have to transfer this energy to the hydrogen to ionize it. And this didn't happen efficiently. So we took what is called the collisional excitation cross sections, right, to see how much you can start transferring the energy from electrons to hydrogen. And it takes I don't know, some millions of years. So it's not a problem for, at least not for photons. Okay. Other thing that can happen is that you can do the opposite. You can have the electrons here, the electrons scatter with the cloud, and it transfers energy to the cloud itself. So what is called upper scatter the cloud. It gives more energy to the cloud, and then this cloud is no longer bound to the black hole and then leaves. Right? You could also, if this would be efficient, again, you could never grow a big cloud, but the cloud would be basically living there. But this again, this is a process that never happens in reasonable time scale. So in principle, you are safe from this perspective. I'm going to give you this couple of not results, but now I'm going to give you the result that is indeed efficient. Okay, and this result has to do with the energy loss that you have when you accelerate electrons. So in principle, you have to imagine that this cloud is a cloud with huge electric and magnetic fields. Meaning that the electrons living there are not going to be just sitting and doing nothing. They're going to be reacting to this electric field, which is rotating. So it's a spinning, so it is an electric field, which is constant for some time. And then the electrons are going to be going back and forward in this electric field. So because, yeah, it has some sign, another sign. The Japanese team computed that indeed these electrons don't leave the cloud. So they are always there because they are, as I said, going up and back and forward. But they are certainly being accelerated in one and the other directions. And what you can compute is what is the typical gamma factor that you acquire from the cloud. And this can be huge. So the typical gamma factor that you acquire is given by, well, by basically the energy density divided by this number. This means that in principle, you are transferring a lot of energy from the cloud to accelerate the electrons, right? And then these electrons will radiate this energy. So you're losing, if you want, the energy of the cloud. And a way to estimate when this is efficiently quenching the growth of the cloud is when the energy that you're losing because you are accelerating electrons equals the energy that you are winning because the black hole is super radiant and you are growing the cloud itself. Is that clear? Yeah, this is a relatively simple process, and what it boils down to is that at these energy densities, 10 to the 19, okay, which are way lower than the per-production and way lower than the final super radiant, this process is efficient. So in principle, you don't grow the cloud. What you do is you accelerate the electrons. These electrons are going to also emit. They emit Compton. Well, in principle, by quantum process, they emit in the X-rays you can compute, but also, since there is a magnetic field, there will be some kind of what's the name? Of radiation that will be even of higher energy. The synchrotron radiation that will be of even hundreds of TeVs. We didn't compute that. Okay, in principle, this would be also another way to look for these signals, and the reason why it's not so interesting, maybe at least at face value, is because this number is much bigger than the number that we had before. So in principle, 0.2 wins. So the idea that as soon as you start growing the cloud, the fact that you have a huge electric field means that the mass is no longer efficient and the cloud leaves the black holes. But maybe for other light bosons, this number 5 is efficient. And then the nice thing is that there is a signal associated to it, given by the fact that these electrons, okay, are going to be accelerated and generating X-rays and even gamma rays with a luminosity which is not bad. All right. So this is the verdict of this first part of the talk. So I'm going to now jump to the second part of the talk. If there is any question at this point, please go ahead.
So when you say other light bosons, you mean like milli-charged dark matter candidates or
for
something?
Instance, yeah. For instance,
it has to be charged under electromagnetic. I mean, has to have a coupling to electrons. Otherwise,
yes,
all the mechanisms don't work, right?
Exactly. Or if there is something like this, or there is other dark matter candidates which are coupled to the plasma, maybe through dipoles or whatever. So it's
Diego, sorry, I didn't understand. But milli-charged dark matter, if there is a dark photon, we suffer from the same problem, right?
In principle, it depends on what you want to do. So in principle, yeah, there is a charge here.
It depends on the coupling, you mean?
There's a coupling, there is a mass of the electron, which is fixed, but you can also think, I understand this in principle is exotic, but there may be ways to rescue this idea. We have not derived any model so far. But the way this scales with the energy, so with the coupling, is different. I don't have it here, but it's different than the way this scales with the coupling. So in principle, there may be some models for which this works. But our paper is more like an result. That's the truth. But anyway, I think it's interesting. All right, maybe I should be more optimistic. Yeah. I'm going to jump now to the second part of the talk, which has to do with the other superradiance, which is connected, but is not connected to the plasma masses, but to the processes coming from a candidate, which is very light by itself. So you don't need to have these other things. Okay. And also I wanted to say about this question, sorry. It may also be true that you may be coupling. So for this, you may have a mass which is not given by the photon mass, sorry, by the plasma mass. It may be given by the the mass of the the photon itself, or the boson itself, and still you will have some of this process will be there for sure, right? It doesn't have anything to do with that. So some of this, yeah, also, you see, it's not that you don't acquire a plasma mass in your fundamental. Well, you will acquire, but maybe it won't be given by this formula. Anyways, as you see, it's not very clear what is the model that for which this may work, but maybe there is a model. Now, is there any way to observe these axions, superradiance in the CMB? That was a question we had. And the idea here is the following. I told you that for low masses, all right, masses which are relatively well motivated by fundamental physics, you may have superradiance if this condition is satisfied. So for astrophysical black holes, you land in 10 to the minus 10 to 10 to the minus 13 electron volts. If you're talking about an axion or a model which is more complete than just the mass, you have to be careful because some of the processes that there may be other processes that modify the cloud, and these processes may have to do with the fact that basically 2 different points. One of them is that this new boson that you have around has self-interactions. All right. So in particular, if it is an axion, you expect that the potential is given by a cosinus of a certain, well, with a certain scale, meaning that it's not only a mass term that is relevant, but there will also be other terms that are relevant, like quartic terms. And these quartic terms mean that as you grow the cloud, you may start to radiate also axions, and eventually there is something called boson-nova, which is an explosion of this cloud. So this cloud grows, but at some point the internal coupling is so high that there is, I mean, the process that you're going to observe is an explosion of axions. This has been studied in the past by some groups. In this talk, I'm going to be focusing on other possibility also related to axions. And it's the fact that if you are also talking about these axion models, in principle, these particles are coupled to electromagnetism. And this is the kind of coupling that you expect. So the FF dual coupling. And what happens is that if A is large enough, you may start producing photons. And then instead of an explosion of axions, this may generate an explosion of photons, right? Or a leakage of photons. So depending on this coupling and what is going on, you may generate a transformation of the cloud into low energy photons. So this is what I illustrate with these arrows here. It has been shown numerically that this happens indeed in this paper from 2 years ago, Ikeda, Brito, Cardoso, and also in this other paper a bit before. There were some more analytical understanding, but the numerics came a bit later. And this is important, this happens for relatively large couplings, but not so large. So couplings which are not excluded, right? And that are still, well, maybe achievable, maybe generating some interesting effects. So when this coupling that I wrote before, this coupling here, is bigger than this number, okay, then it is believed that the main aim of this cloud is that it is going to generate an explosion of low energy photons. Okay, and this has to do with the resonant conversion of these axions into this low energy photon. How much energy is extracted? Well, in principle, you can extract all the energy of the cloud, but this is not efficient. In principle, what seems to be happening is that you extract a percentage of it. So let's say this number, which is quite big, right? But multiply by 10 to the minus 4, 10 to the minus 6. So in principle, there is a large amount of energy extracted in a short time, in a short amount of time, in terms of low energy photons, and this is going to be, leaking into the environment around it. You have to be careful, also, as before, because this black hole is not living isolated; it's living surrounded by some plasma mass. You need to make sure that these photons, whose wavelength is more or less the quantum wavelength of these guys, you have to make sure that these photons are able to propagate. Otherwise, they will just, you know, keep here. So if they are not able to propagate, they will stay around here. That means that in principle, you have to make sure that the mass is kind of bigger than the plasma mass around the black hole. So this, in other words, is efficient for axion masses which are above this 10 to the minus 13 eV, which is a typical typical plasma mass in the intergalactic mediums. All right. So from the same concept that we had before, now we have these photons leaving the cloud, and they have to satisfy basically this condition. All right. Now, what happens with these photons? So you see, this is the same I wrote before. So these photons meet free electrons. These free electrons scatter with another free electron, and this, what is called free scattering, hits the electrons around the cloud, right? And this has some rate, the free electron, that has to do with the number of photons, number of electrons, some cross-section. This cross-section is quite standard in galaxy formation. Okay, it's one of the things that you know, is in the books. And eventually, well, it's given by some Thomson cross-section, so it's not important. The important thing is that eventually it's very efficient, and you can, for the numbers I gave you before, deposit all the energy of the, you know, of the cloud in less than 1 parsec. Okay, because you are easily absorbing it in the electrons. That means that you can make the calculation that this means that these electrons are heated to a huge temperature, 10 to the 12 Kelvin. So what you have now is that there will be a shell, kind of shell of very, very hot electrons, right, propagating outwards. And this is the kind of situation where you expect a kind of shock wave to develop. So I don't know much about shock waves. We only took this idea that you will have a very hot, sorry, let me go here, a very hot environment surrounded by a cold environment, and this will be expanding with a certain velocity. This is what we're going to solve. Before we go there, let me tell you when this happens. So I told you that this is going to happen for certain couplings, all right? It's going to be happening for masses which are higher than the plasma mass, and also it's going to be happening for masses that are lower than a certain mass. If you go to higher masses here, the mean free path is too long, meaning that this is not so efficient, so you don't hit so much the environment. So it's for a, well, this area is kind of informative, but it's not super precise, but you expect that this for this area, you're going to have this shockwave develop, and now we're going to study what happens with this shockwave. Okay, so the shockwave is basically, as I said, a very hot amount of electrons propagating, and there will be, the force is given by the pressure, so there's a pressure force here. There is some braking because you have to accelerate this material. This formula, we took it from a very old paper on shock waves generated from supernova. And then there is also the fact that, well, you have to accelerate the material here, and also you are pulled back because there is some gravitational acceleration. So there's deceleration in this case, right? What do we need? We need to know the pressure as a function of the energy. We assume that this is a relativistic plasma, okay, the pressure here. We need to know how much energy I am injecting in the process, and this is given by a conservation of energy. So there will be some luminosity, so the amount of energy injected by superradiance by these low energy photons. So this is the luminosity. Then it will be also the possibility of this wave here scattering with the local environment, and this can go either way. It can be either given plus or minus energy to the environment. Okay, and this is something that we are not very certain about, but we have shown that it's not very important. Then these electrons are going to be cooling because they interact with the CMB. Okay, there is the so-called quantum cooling. They are also going to be emitting thermally, so thermal bremsstrahlung, and they are also going to meet the neutral hydrogen around, ionize it, and lose energy. So this is a kind of a complicated process. I think we put everything that is relevant. Maybe, well, we were talking to experts on this reionization stuff like Jens Gruber, and he was kind of okay with that, so that's fine. What else do we need in the energy conservation? So there is the luminosity, and then of course you are expanding, okay? So you need to put also this other term here with the pressure. And now you see that we have everything we need to solve the equation. So we need the pressure, and now we have the pressure as a function of time also, so everything is self-contained. We go to the books on astrophysics, high energy astrophysics and cosmology that allows us to know what these different luminosities are. And here is the result, okay? After some numerics and some checks, what we have done here is to see what happens if a 10 to the 3 solar mass black hole generates this burst at redshift 15, or a 30 solar mass black hole generates this burst at redshift 6. And those are the kind of black holes that are efficient at these two different redshifts that correspond to two different plasma densities. So what happens in both cases is that they start the cloud, sorry, this shock wave starts from basically 0 and starts to grow. So this is the radius of the shock wave, and eventually generates a very large, okay, a very large bubble of very hot medium, right? So we're generating a very hot and ionized bubble of a megaparsec scale. And now you may wonder, what are the consequences of these guys? And this is going to be my last point. So there are many consequences which are possible. In particular, you have more than one event. So you think that there are several of these black holes populating the universe. They may have a global impact. Let's focus on a single event and leave the distribution for the future. I'm very happy to, yeah, as I said, talk about this. But it's something that we are now investigating. So a hot and ionized large bubble is going to generate what is called a CMB spectral distortion. And how does this happen? So it happens that if you have a certain black body spectrum, it goes through a hot plasma, the spectrum is modified in the following way. So the difference in the temperature of a particular wave number in the spectrum is going to be modified with what is called a Y distortion in this case. And the Y distortion means that I take photons from low energy and put them in the high energy. So I am, reducing the number of photons in the low tail and putting them in the high energy tail. So that means that I distort the CMB black body spectrum, right? That goes through these very big bubbles along its way from the CMB to us. To which level? Well, here it is. This level is quantified by a certain number called Y. It has to do with the temperature of the bubble and some physical processes. And the important thing for us is that what this number is when these CMB photons go through these clouds generated by this burst of the black hole. And you see that what you generate as a function of angle, because in principle, these are big guys, right? These are 30 megaparsec in the sky, are distortions which are relatively big. So 10 to the minus 4, 10 to the minus 3 have to be compared with those that you expect from astrophysical backgrounds, which are much smaller. But these angles here are not currently, experiments are not able nowadays to go to these small angles at this precision. So we believe that the next generation of CMB experiments will be able to detect these kind of distortions at this small angle. So remember, the small angle is because you have a 30 megaparsec, some megaparsec cloud, bubble at different redshifts, right? So this determines these angles. But it's something that has to be investigated further, okay? It's something that, we talk to experts on this and they say, yeah, this is possible, but these missions are not yet approved, let's say. So it gives an extra motivation if you want for this CMB4 or even further, CMB6 or whatever missions. Another observable consequence of these big clouds or these bigger bubbles is that since you have more electrons So what you are doing is that you are ionizing, right? You are as this cloud expands, you ionize the surrounding material, so the number of free electrons is going to be higher in these bubbles. So you also modify the optical depth of these areas. And optical depth is also an observable that can be and is measured by the CMB missions. The modification that we make is such that it is, in principle, higher than what Planck can do, but this is a bit cheating because this is what Planck can do for the whole sky coverage. Here, what I'm telling you is that in these small areas of around one arc mean, the optical depth is modified to levels which are in principle okay, but Planck has not been able to measure it. Again, you need next generation maybe to reach this single event. The reason why I compare with Planck is that if you have more than one event, then this will be accumulated in the sky, and then in principle, yes, you can say that there will be an average effect that will generate these changes in the optical depth. But for one single event, even though the effect is very big in one particular direction, yeah, this comparison with Planck is not completely correct. Okay, so because Planck does this, achieves this very low number by taking into account the whole sky. So, but maybe this is not so bad for next generation. And yeah, it's a miracle that I'm on time. I think it's the first time in many years. So my conclusions are that, well, this rotational superradiance has been used as a unique handle into the physics of light bosons. These light bosons can have two origins. One of them is that the mass is given by the plasma mass, and in this case, most likely is not so interesting because, well, before our works this year, it was thought that the pair production would quench this process. Now we know that even way before that this happens, the fact that there are huge electric fields generate a modification in the plasma mass. So this is not, this happens. But even these other possibilities of accelerating the electrons around the cloud are also going to be important at also a way. At times, way before the whole way before the whole cloud, the bosonic cloud develops. So in principle, this is an interesting idea, but maybe we need to go for physics beyond the standard model to make it work, not for the standard photon, which is a pity. The second point of my talk was more optimistic and was having to do with the fact that another way to quench the cloud, you see that precisely here, you see why model-dependent things can be very different depending on which model. In this case, the cloud is quenched because the axion is decaying into photons. And this leaves a signature in the CMB observables having to do with the fact that these photons are going to be absorbed by the surrounding medium. The surrounding medium will heat up and will generate a very large bubble of ionized and hot plasma. And I think that's all I wanted to tell you, so thank you very much.
Okay, thank you very much, Diego, for your talk. Okay, now, is there any question?
I have a question.
Go ahead.
So, if I understand well, so these spectral distortions or these distortions of the CMB, these are CMB photons that are scattered by these ionized hot clouds that you produce at lower redshifts.
Yes.
And so, are there other? I mean, I know nothing about this. Are there other astrophysical processes that produce you disentangle?
Yes, and indeed, these spectral distortions are used as a way to study cosmology. Well, they are in the future, in principle. There are missions to try to measure them. For instance, it's very important for hot clusters. No, it's telling you it's telling you how ionization happens and how you can have some patches of the sky which are colder or hotter than the others. However, the astrophysical backgrounds that we expect are at this level here. So are below the
Okay.
at least for standard process.
This leads me to my next question. So if this happens, suppose this process happens, in fact, before ionization, when the universe is neutral, would these very large energies, even though they're low energy photons, but still there are many of them, would they be giving a contribution to the reionization of the universe?
Yes, but for this you need to understand better how many of these black holes there are, I think.
Okay, yeah, fair enough. Well, even for the spectral distortions, right?
Sorry?
Even for the spectral distortions. You
for
must be
spectral
making some
distortions depends
assumption.
on your sensitivity. So in principle, if you have sensitivity to small angles,
okay, so you just see the effect of one source, you mean?
You can see one source, which is quite amazing. But if not, you can also try to do the average, and you know more.
Okay, oh, that's very nice. Thank you.
Yeah, and I think that maybe you can help us with this.
Maybe or maybe not. Well, let's talk about it.
Okay, any other question?
Diego, I have thanks for the nice talk. I have a couple of questions actually. So first of all, like everything here is happening during reionization, right? It is pretty complicated period, right?
No, it's before or after. You see, we have taken precisely.
Well, I mean, this is also what I'm confused about, like, because like, for example, like you say, like also in the first part of the talk, you put reionization at z equal 10, right? But start to form much earlier. So for example, what we did in other words, I mean, we excise a region of redshift that is much larger than this, like it's like between 6 and 20, not 10, while you were putting the bound at 10, right? Yeah, exactly. If you go in the next plot, then the next slide, here you are putting reionization at 10, but start to form at 20 or so, right? So really also that other region I mean, there are a lot of Lyman alpha and UV photons up, and reionization is already like, things are already happening. So I was wondering how much you rely, in this region, like 10, 15, and how,
It's not very important, I think, Andrea, because you can start, as I said, well, this is basically what we want to, I think you are saying basically that this is one, but there is in principle, there is some dispersion in this number. No?
Right.
So that means that, see, this happens relatively fast in astrophysical times. It's enough that one of these 10 to the 3 solar mass black hole lives in this environment. If we want to do the next step of these populations, then I understand it's going to be a bit harder because we need to know more about when this happens, and that's why the next part of the project is more challenging.
I see. And it's like the second question that is related to the second part of the talk, and you say that you have two limits for the axion mass, right? One that is given by the plasma frequency, exactly this one. So you're generating these shock waves on scales. So you're generating this bubble or like megaparsec stuff. But I would say that if one just think about like the gene scale or whatever, you will have oscillations or much like smaller scales, right? So did you check like the oscillations that you are saved by the same log normal or Gaussian that you were taking before, right? It's giving you some oscillations of the electron plasma density, right? So the 10 to the minus 13 that you were taking is the homogeneous one, right? But you have oscillations and under and over density.
No, but this parsec is the megaparsec is the final result. We start at parsec. So you deposit all this energy of the cloud in a very small region, and then this basically booms.
Okay.
So what I mean, then it doesn't really matter what is below outside, because this is a 10 to the 12 Kelvin cloud expanding, and then it doesn't really matter. I think what.
Okay.
Maybe let me see.
You're saying that it doesn't matter if then after that you will encounter, let's say, a region in which the plasma density is larger.
Maybe it changes a little bit this last term here and this part here, because in principle you have to accelerate more electrons or less electrons, but yeah, I don't know. Let me see. We take this into consideration a little bit with these 3 lines.
Mm-hmm.
This FD and FM also are internal numbers that tell you, what happens when you interact with the electrons that you are accelerating here,
Mm-hmm.
and this heating from collisions with medium. Okay, and in principle, well, yeah, it enters, but it doesn't really change the picture too much. Well, I agree. It's an uncertainty. It's an uncertainty.
Okay, that's cool. Thank you.
Okay, so some other question? Okay, if not, let's thank Diego again for this nice talk. And